Uh, got a couple people who do or used to. So, all right. So today we're going to solve a wave equation associated with a stringed instrument. And although I have tended to do a lot of my examples um, using specific functions and specific numbers because students seem to like it better, today I'm actually going to do an example where we don't specify the length of the string, where we just call that L. All right. So we're going to solve the problem in general terms, uh, where we have boundary at 0 and a boundary at L. So I'm going to say U of 0 and T. And I'm going to give this problem homogeneous Dirichlet boundary conditions, which is sort of the typical case in a stringed instrument. The strings are fastened at each end of the instrument, whether that be a fretboard or a fingerboard or whatever the name of that part of the instrument is. So these are the two boundary conditions. Nothing fancy here in the governing partial differential equation, just the two time derivatives and the two space derivatives. This is a vanilla wave equation. And let's see. Oh, you know what I'm also going to do? I'm going to put a c squared in there. Where remember that c is the square root of tension over string density. All right. And what else? Then I need two initial conditions. And I don't really care what that initial condition is. So again, I'm going to do something kind of generic. I'm just going to call this I0 of x. It's just some function. Okay. It doesn't really matter what it is. And then initial value of the time derivative. For simplicity, I'm just going to make equal to 0. Yeah, that's fine. So this is characteristic of like a plucked string, a plucked instrument, um, where I have some initial displacement of the string, and then I let it go, and the system then evolves according to the wave equation with a constant c squared here.
Do we need
If I
four?
were really trying to model, other kinds of instrument like a bowed instrument, um, then the action of the bow might show up as, instead of a initial displacement of the string, it might show up as a continual, forcing function over here or something like that. But I'm not trying to be too complicated. I just want to get like basic properties of this equation in the case of a stringed instrument. And the simplest way to get something that's not 0 is just to have an initial displacement. Do we need 4 initial conditions because of the UTT? Okay, so we need 2 conditions because of the 2 x derivatives, and that's these two. These are our 2 boundary conditions. And then we have 2 time derivatives, and so we need 2 initial conditions. And that's what these are right here, right? And these are initial because they take place at t equals 0, right? Here you've got your t equals 0. And these are boundary because they take place at x equals 0 and x equals L.
Awesome, thank you.
Yep. Okay, so let's go ahead and solve this. All right. Like all problems in this class, the key thing is to identify the whoops. Want to get my pen back. Identify the spatial operator, and it's right here. Right? Got our time derivatives over here. It's not part of the spatial operator. We're going to call this the spatial operator right here. So we're going to define LU equals c squared UXX. Now, there was some discussion on the homework, do I need to include the C squared in the spatial operator? And it's a good habit just to go ahead and do that. Under certain circumstances, if you leave out the C squared, you get the same answer, but I don't really want to go into that. So the simplest response is just to say, you know what, that's the spatial operator, anything multiplying it, we go ahead and keep that. So let's do that. Let's just work on that. All right, this operator is just a constant times uxx, and we know that uxx is already self-adjoint. We know that its weight function is just 1, so that very much simplifies our life. So stringed instrument. So the next thing we do is we look for the eigenfunctions. We want the transform in order to transform this PDE into an ODE, and to do that, we find the eigenfunctions. All right, now the eigenfunctions satisfy LU equals L phi equals minus lambda phi, always. And here LU is C squared UXX, and so L phi is going to be C squared phi XX plus lambda phi equals 0. With boundary conditions given by the boundary conditions in the original problem, Dirichlet boundary conditions, phi of 0 is 0, phi of L equals 0. All right, and so we've seen this many times. We guess e to the Rx, it's constant coefficient second order ODE, so we guess e to the Rx. We get C squared R, so let's go ahead and say that, guess e to the Rx. We get C squared R squared plus lambda equals 0. And so R equals plus or minus the square root of negative lambda over C squared, which I guess you could say plus or minus the square root of negative lambda all over C. C squared is always positive, so we can always take its square root. We just get C on the outside. All right, and as usual, there are 3 cases. And also, as is often usual, I'm only going to consider one of them for simplicity and time's sake. I'm only going to consider the case where lambda is larger than that dividing case. I can confirm that we will not get any eigenvalues for lambda equals 0 or lambda negative. That's worth checking, but not going to do that today. So when lambda is positive, we can pull this minus sign out. All right, and those are our values of R. That gives us phi of x is C1 cosine root lambda over C x plus C2 sine root lambda over C x. And then we have our first Dirichlet condition, phi of 0. Since sine of 0 is 0, the only thing we're going to get is this C1. And the boundary condition tells us that that is 0. Then we have our second condition at L. And since C1 is already 0, we know this term's not going to be present. So all we're going to get is C2 sine root lambda over C times L, which will be 0. Okay. And as usual, we would prefer not to set C2 equals 0. That would give us a trivial solution. So we require the argument of the sine function to equal one of its roots. All right. And so those roots occur at n pi. And if we now solve for lambda, we're going to get lambda sub n equals n pi c over L quantity squared. And our eigenfunctions are going to equal, if root lambda over c times, if root lambda over c equals n pi over L, then we're going to get sine n pi x over L. All right. And so there are our eigenvalues and eigenfunctions. Okay, so this tells us in turn what the transform is going to be, right? What is the transform pair? The transform of any function of x is going to be the integral from 0 to L of that function of x. Oops, sorry. Transform is the integral of 0 to L, that function of x times sine n pi x over L dx, divided by the integral from 0 to L of sine squared n pi x over L. And then to recover the original function, we will sum up n from 1 to infinity those coefficients times the associated eigenfunctions, just like usual. All right, so this is our transform pair. It's always worth writing down. All right, now we take the transform of the original problem. All right, and so we get the transform of UTT. Just a sec, I see a question over there. Yes, go back to the last page for a second. I will post these right after class, but I'm happy to go back. Rachel, can you turn off your microphone? Sorry, I didn't mean to single you out. I went to a online colloquium the other day with like a very well-known mathematician. That's okay. So I did exactly the same thing the other day. I showed up about 5 minutes late to an online colloquium in my department with a pretty well-known mathematician, and I forgot to turn off my microphone. And so I'm sitting there, and my kids are in the background, like arguing about Minecraft or something. And she just pauses, and she's like, "Can somebody turn off their microphone?" And it was me, and I felt really bad. So you're not alone.
That's embarrassing.
All right, so here's our transform pair. Perfect. Go back. So I've got my problem, my partial differential equations that I have to take the transform of. And then I don't have to take the transform of the boundary conditions. They only occur at the boundaries, so they don't really depend on x. But those initial conditions depend on x. And so I need to take the transform of them as well. So I have u of x0 to take its transform equals this function I naught of x. And I have to take its transform. And then I have the time derivative equals, and our problem, that was 0. Take its transform. Ah, yes, thank you. Thank you. Problem was c squared uxx. So I take its transform, all right? And again, I keep all that. I don't pull the c squared out because that's part of the operator, and the whole point is to take the transform of the operator. So what do we have here? I have the transform, which remember is an integral in x of the time derivative. And when I have integral in x, derivative in time, x and t are independent variables, I can change that order of operations. And so instead of taking the transform of the derivative, I can take the derivative of the transform. And I get u n prime prime, where those primes stand for time derivatives. Then over here, I have the transform of L acting on U, and that's always minus lambda sub n U sub n. Here I have the transform of U evaluated at t equals 0. So I have these two operations, evaluation at time t equals 0, transform in x. Again, x and time are independent variables, so I can change that order of operations. I get un of 0. Now, instead of first evaluating, then taking the transform, I am first taking the transform, then evaluating. Equals I0n, I'll call that, right? And this is just some number, right? This is some function of x. We got another microphone on, Alex. Thanks. This is just some function of x. I take its integral transform. I just get some number that depends on n. Okay. And then I do the same thing here. In this second row, I have another initial condition. I've got evaluation, then transform. I can do transform, time derivative, evaluation. I can change those orders of operations. And this is just going to be 0 because the transform of 0 is 0. All right. And so what I have right here is a fairly simple ordinary differential equation with two initial conditions, second order ordinary differential equation, two initial conditions, right? That next step, solve the result. In chapter 2 and 3, the result was an algebra equation. In chapter 4, the result was a first order ODE. And in chapter 5, the result is a second order ODE. All right. But in every single one of those chapters, we can label this step solve the result. It's just a little bit more simple in chapters 2 and 3. All right. So I have un prime prime plus lambda sub n u sub n equals 0. I can solve this. This is a constant coefficient second order ODE. If you don't remember what the solution is to this specific form, you can just guess, right? Guess u sub n equals e to the r t. Now we're doing time derivatives in this transform problem. We get r squared plus lambda sub n equals 0. So r equals plus or minus the square root of negative lambda sub n. Now we've already found the lambda sub n. The lambda sub n are all positive. And so this is purely imaginary pair. All right. And we know that a purely imaginary pair gives us u sub n of t equals c1 cosine root lambda sub n t plus c2 sine root lambda sub n t. And this happens to look quite similar to our solution to the eigenfunctions. That's kind of coincidental because right now we're solving a time problem that just happens to have sort of the same form. All right. So don't get too confused by the fact that it looks similar. You know, am I doing something wrong, or does it always look similar? You know, we're very, very likely to see patterns where, you know, it's what's it called? It's called overgeneralization. Like this looks the same, but don't generalize to assume that it's always going to look the same. It just happens to in this problem. Okay, and so now we have our initial conditions. Un of 0 equals what? Sine of 0 is 0. So we're just going to get C1, and that's going to be I0n. And then I have un prime of 0. Derivative of cosine is negative sine. Sine of 0 is 0. So this term's not going to be present in this boundary condition. I'm going to get C2 square root lambda n cosine of 0, which is 1. And that's just 0. All right. So C2 is 0. C1 is I0n. And my un of t equals I0n cosine lambda n t. And I'm now ready to invert. My general solution, u of x and t, is going to be the sum, n from 1 to infinity, of I0 sub n, these are just numbers, right, times cosine. And let's go ahead and write this out. What is lambda sub n again? Root lambda. Root lambda is n pi c over L. N pi c t over L.
I got n pi c over L squared. For our eigenvalue.
Yeah, that was lambda. Lambda is n pi c over L quantity squared. But what we're looking for is root lambda.
Oh.
Right?
All right, sorry.
Yep, no problem. times the eigenfunctions, which are sine root lambda x and pi c over L x. All right, and here's our general solution for the wave equation with just an initial condition, no forcing function, no homogeneous Dirichlet conditions, right? It's very simple setup, but it leads to a nice simple solution. Now, I want to do a couple of things. I want to talk about this solution at some length because it really tells us a lot about if you've ever had an interest in stringed instruments. It really helps us understand a lot about stringed instruments and why they work the way they do. And in turn, if you're at all familiar with a stringed instrument, I think the intuitive knowledge we have about stringed instruments helps us understand the wave equation a little bit. But first, let me go ahead and bring up a movie that I made where the initial condition where L is 2. So I'm going to play a movie. All right, where L is 2 and my initial condition is just a triangle. That is x on one side and 2 minus x on the other. All right. And you can go through, the eigenfunctions in this case are phi of x equals sine and c is 1 and pi x over 2. And then, this is my initial condition. And so my I, 0, n is going to be, how do I calculate the coefficients for this initial condition? I have to split my top integral into 2 pieces since my function is discontinuous. I have 0 to 1 of x times sine n pi x over 2 dx plus the integral from 1 to 2 of 2 minus x, and I'm running out of room. Sine n pi x over 2 dx, but then in the denominator, right, my eigenfunctions are nice and smooth, so I don't have to break my integral into 2 pieces. I just have the integral from 0 to 2 sine squared n pi x over 2 dx. Okay, and so I've gone and calculated these numbers, and I don't really want to waste our time calculating these numbers in class. I just want to show you the movie. So let's see, where is that? Okay. Now I need to figure out how to share different window. Why is it not in the list? Ah, here it is. Here it is. Okay, so now you should see this little movie window screen. And here is the result. This solution to the wave equation. You can see I start off with this triangle, and then at time t equals 0, I let go of the string, and it kind of collapses back down toward, the plane in which it likes to live. It's definitely oscillating up and down, but it's doing so in kind of a weird way, um, which is sort of characteristic of um, the way functions with sharp corners oscillate. It's kind of collapsing in this sort of strange way. So here's the solution. If you take a stringed instrument like a harp or something, and you pull the string out of the way and you let it go, this is what it's doing very quickly. So you can't really see this, but if you took like a high-speed camera and you visualized, the shape of the harp string after you let it go, this is what it would be doing. All right. So that's one thing I want to show you is we can solve these problems and we get these series solutions and we can plot them and they can we can actually look at them and learn something by looking at the visualizations of these solutions. But then I want to talk about uh, does anybody have any questions? Actually, I haven't been good about asking that lately. Before we move on. No questions. Okay. All right, I'll close that. Now what happens? Now I need to go back and share this window. All right. Let's talk about this solution a little bit. I'm gonna copy and paste it again. Where'd it go? I don't know. I don't know. How about this? There we go. There's a copy. Okay. So you have all these different I want to make a couple of comments. You have all of these different terms, right? And they correspond to different shapes of fluctuation in the string. All right. So the n equals 1 term, the first term in the series, right, has a spatial shape of 1 sine wave. Hang on a second. I think I made a mistake somewhere here. I did. All right. Look, the spatial eigenfunctions are root lambda over c times x. And so there's no c in there in space. So that was my mistake. I was just copying down what I saw over here, but there's no c there in the eigenfunction. Sorry about that. Right? There is a c here. There's no c here. All right, and the same is true right there. So this is the shape of that first term in the eigenfunction expansion. And it kind of oscillates with some frequency, right? If this number here is called the wave number, the number of sort of oscillations that fit in a box. This number right here is called the frequency. All right. So the frequency is n pi c over L. But remember, c is defined in terms of the tension and the density. So it is n pi uh, square root of uh, tau over rho, all divided by L. And if n equals 1, then I just have pi. And in fact, I don't like how that looks, so I'm going to write just pi over L square root of tau over rho is my frequency. Okay, now that's just one of the terms in my solution, right? At the same time, I have a second term, and it is sine 2 pi x over L. And so it oscillates twice. It looks like this. Okay. And its frequency, there's going to be a 2 here. And so I'm going to get 2 pi over L square root of rho. Sorry, tau over rho. And then the next term in my series is going to have 3 oscillations. All right. And it's going to have frequency 3 pi over L square root of tau over rho. Now, when I'm teaching this class in person, I like to bring kind of a rope or a cord to class and have students get pairs of students to stand up in front of the class and hold both ends of the rope. And if you're doing, say, you're doing jump rope, right? You've got 2 people doing jump rope. You want to swing the whole rope around in a circle, and you want it to be this shape right here that's just going around in a circle. And so there's this little sort of negotiation that happens between the two of you, unspoken, where you kind of home in on the right frequency to turn the rope. And you know that if like you turn it too fast, you don't get a nice shape like this. You get sort of something that doesn't look like a jump rope at all until you both kind of instinctively home in on what ends up being uh, this frequency. Okay. And once you find this frequency, you find that the shape of the rope that you get looks very much like a jump rope. But if you take what we've just learned, this knowledge of how the wave equation works, um, and you find this frequency, all right, and you time it in your head, and then you and your partner say, okay, on the count of 3, we're going to double that frequency. We're going to try and go exactly twice as fast as the frequency that gives us a nice jump rope shape. You can actually get the rope to do this, right? Where, as if by magic, this point in the middle just doesn't move. And you have the two of you swinging the rope, and one piece is like this, one piece is up while the other piece is down. And then when your side goes down, the other side goes up. Right. And so this is like a fun game. If you're like trapped in quarantine with a friend or something, go get a rope, a relatively heavy rope. Just a piece of string isn't going to work. It needs to be something you could actually jump rope with. And like, try this, right? Get one of you on each end and get this natural jump rope shape working. Figure out that frequency, time it, and then cut it in half. Uh, Shake that rope twice as fast, and you'll get this thing. It's pretty easy once you know what to do. It's pretty easy to make this happen. Um, if you're real careful, and instead of doubling that frequency, you triple that frequency, you can get this shape to appear. You used to do that in elementary school. There you go. Yeah. And well, like I said, this is very achievable if you especially if you understand the math and okay, I just have to use twice the frequency of the one that gives me a normal shape. This one's pretty easy to do. This one's not so easy because there's a lot less room for error. But if you triple that frequency, you can get this to show up. So where you could have 3 people jumping in the middle of the jump rope. All right, one in this little region, one in this little region, and one in this little region. The ones on the end would be, jumping at the same time, and the one in the middle would be jumping in between them. And similarly, this goes to infinity. For n equals 4, it's 4 pi x over L. And so you would get this sort of shape going, where this is fixed and this is fixed and this is fixed, and that has frequency 4 pi over L, tau over rho. Okay, so this is one thing to understand about what's happening during the wave equation is you have this type of shape vibrating at this frequency. This next type of shape, the next term in the series is vibrating. It has twice the number of bumps and it vibrates at twice the frequency. The next term in the series has 3 times the number of bumps and it vibrates at 3 times the frequency. The next term has 4 times the number of bumps and vibrates at 4 times the frequency. Um, so that's one thing to understand. And if you've ever listened extremely carefully to a stringed instrument, um, in a very nice, high quality stringed instrument in a place without much distraction, what you realize, or if you've ever, not that any one of you have ever done this, but if you like subjected the output of really any instrument to a time frequency analyzer. If you took the Fourier transform of the output of the instrument, what you find is that yeah, the instrument is producing a note at this frequency, right? That's called the base frequency. But if you're listening very carefully or you mathematically decompose its output, you'll find that it's also simultaneously producing something at twice the frequency, 3 times the frequency, 4 times the frequency, 5 times the frequency, and so on. They're just not quite as loud as the base frequency. And so what you hear is that base frequency. But all these other frequencies are also present at the same time. And the reason they don't necessarily jump out at you is that they are all these frequencies are they sort of play well together. Yes, yes, that's exactly right. It's called the harmonic series. Thanks, Wade. And so, does anybody know what happens if you double the frequency of what happens? How does it strike your ear if you double the frequency?
Doesn't it go way sharper?
Yeah, it goes higher, but it goes higher by an amount that we call an octave, right? So if you double the frequency of a note, it sounds 1 octave higher. Okay, which is pretty cool. Then if you quadruple the frequency, it sounds 2 octaves higher. If you multiply the frequency by 8, it sounds 3 octaves higher. So what's really cool is that our ears naturally perform what you would call mathematically as like a Fourier decomposition, right? So they naturally sort of take the log base 2 of frequency and convert a linear scale into a log scale so that every doubling of a frequency your ear interprets as a 1 increment in the octave. They do the same with volume. If you double the amplitude of something, your ear interprets it as like 1 unit louder, and then you have to double the amplitude again to get 1 more unit louder. And so it turns out that pretty much all of our senses act this way. They very naturally sort of take the logarithm of the strength of the input. When you go from inside a dark house to outside, the light level changes by like a factor of a million. But your eyes, don't explode. They sort of readjust. They're like, oh, this is several units brighter, and that's because your senses basically all take logarithms of their input. And there's a rule for this, I think, in like biology. I took very little biology, so I don't know the name of it. But if anybody happens to know the name of this like rule or observation, I'd love to be informed. So that's one thing, is that you have this sequence of notes called the harmonic series. Uh, Single time the frequency, twice the frequency, 3 times the frequency, 4 times the frequency. They all kind of sound nice together. It so happens that I have a piano in this room. So I'm going to go try and pick out a harmonic series on the piano. We'll see. And I can't take the microphone all the way over there. So we'll see how well you can hear it. But, I'll do my best here. Just a second. All right. All right. So that's the harmonic series. It's not super exciting, but all those notes, sound kind of nice together. They're like da 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 da. And if you've ever played like a trumpet, brass instruments, they're very much focused on the harmonic series. So that's an interesting thing to know about the wave equation is that anytime you play one note, you have these other notes that are also happening called overtones, and they obey the harmonic series and they all sound but play more. That's about all I can play. I don't play the piano. I play the viola. I played for 10 years, but my viola is like super broken right now because I haven't played it in like 5 years. Okay. The other thing to know. Okay, so that's what happens when you change n. Okay, thank you. That's what happens when you change n in this series. Okay, but there's a couple of other parameters in this solution that it's worth thinking about. All right. Another important one is L. Now, there's a reason that I didn't specify L because what happens when you play a stringed instrument? So, like I said, the viola, the greatest of all stringed instruments, or the cello, or like the guitar, or the erhu, or there's like one more that I'm always forgetting. Oh yeah, the violin. Um, so what happens when you play any of these instruments is that you put your fingers down, and when you put your finger down, you change the length of the string. Okay, normally the string is anchored at the left hand side and the right hand side, but if you put your finger down partway up the fingerboard, you have now changed the length of the string, and only this part right here is vibrating. And then this part is sort of just hanging around there. Okay. And so you've effectively changed the length of the string. What happens when L gets smaller? When L gets smaller, the frequency increases. Okay. And that's how you change the pitch of a string instrument is you at least the instruments where you put your fingers down on the strings, like the ones I mentioned, you are changing the value of L, which increases the pitch on the string. In particular, if you put your finger exactly halfway in the middle of the string, then you have cut L by a factor of 2, which doubles the frequency, which sounds 1 octave higher. Okay, and so this is like a very well-known fact. Anyone who plays a stringed instrument, that if you put your finger down right in the middle of the string, you increase the pitch by an octave. Okay, for exactly the reasons that we just talked about. So other instruments don't change the length of the string. So a piano, just has all different strings, which all have different lengths. Okay, so a harp also has all different strings with different lengths. So some instruments you actually change the length of the string. Some instruments you just use a different string. Uh, in addition, you have here the tension. If I increase the tension, I increase the frequency. And this is how you tune a stringed instrument, is they all have like a screw on one end, and you can turn that screw to increase or decrease the tension. And that is how you tune an instrument before you play it, right? By adjusting the tension. You can't adjust the length because that's dictated by the shape of the instrument, but you can change the tension. Finally, another thing that you find is that if you increase the density, this frequency decreases. All right. And so if you look at stringed instruments that can cover lots of different range, you find that, pretty universally, the lower pitched strings are thicker. All right. They're wound with more layers of steel or whatever the strings are made out of. And that is to increase the density. So if you ever look inside a piano, piano covers like 8 octaves, or yeah, I think it's about 8 octaves. And so if you only relied on changing the length of the string in a piano, your highest, your lowest pitch string would have to be 2 to the 8th power longer than your highest pitch string, right? Which is 256 times longer. And you do not see this in a piano. The highest pitch strings are in quite a bit shorter than the lowest pitch strings, but they're not 256 times shorter. And the reason is that in a piano and also like in a harp, you're also changing both the density and the tension of the strings in order to get those different pitches. It's kind of the same principle, unlike a violin or a viola, cello. You have four strings, which vary widely in pitch. The length of them all is fixed. And we don't just crank the tension up by a factor of like 1,000 between the lowest string and the highest string. That would be dangerous. If the highest string snapped, you'd kill yourself if it was under that much tension. And so the way that we get all those different pitches on the same instrument is to vary the density of the strings. Um, I am definitely a stringed instrument snob because I played stringed instruments. But if you played some other instrument, a wind instrument, a brass instrument, I would just observe that all of these instruments are basically one dimensional vibrating columns of air. Okay, not vibrating strings anymore. But if you look at all these instruments, they're basically all long and skinny. The flute is the best example, but a clarinet is just a vertical flute with a weirder mouthpiece. Uh, a trombone and a trumpet is just a flute like wrapped around itself, so that you can fit a greater length of instrument into the same size of three-dimensional space. Really, all the instruments in the orchestra are one-dimensional vibrating something. Okay, whether that be a string, a column of air, even the xylophone, those a lot of the percussion instruments are just one-dimensional, sticks or metal bars. Or chimes, the big tall metal circles that are kind of vibrating. All these things are just one dimensional vibrating objects. And this is important because the nature of the one dimensional wave equation is that it has these very nice properties that when you can cut the length in half to double the pitch, and importantly the fact that the overtones follow the harmonic sequence is the reason that all these instruments sound relatively nice, um, except for violins. But no, I'm just kidding. Um, all these instruments sound fairly nice because they are one-dimensional vibrating columns of air. And it turns out that if they had more dimensions, or they weren't one-dimensional, they weren't so simple, then their overtones don't sound nice. Okay, and that's why all instruments are basically one-dimensional columns. Yeah, I know. I'm sorry. I'm sorry. You gotta stay loyal to your people. Um, so that's about it. It's 11:50. There's a lot here. Um, and having spent so much time myself, playing a stringed instrument, I love to kind of walk through all the effects of these constants, because like once you understand this equation, then you're like, oh, now I understand. I know. I'm so sorry. Uh, Pianos are stringed instruments. It's a vibrating string. Yes, there's a hammer, but the hammer hits the string. Um, I mean, okay, you could say that you could have a philosophical discussion here, but a piano is still based on the idea of a vibrating one-dimensional object. The only thing in the orchestra that is not are the timpani, and that's why timpani they don't they're harder. You can sort of tune timpani, um, but they don't really have like pitches in the same way that other instruments do. So, does anyone have any questions about any of this? We'll get back to like regular calculating boring things in the future. But this is one of my favorite lectures because it really connects the math to like something that a lot of us have some experience with. And as usual, I'm welcome. I'm happy to hang around a little while if you do have questions or want to talk more. If you, especially on this topic, if anyone has a question, you're welcome to unmute your microphone and ask it. But it is 11:50, so if you need to go, that's perfectly fine.